All right, so 6.3 is going to introduce you to a new notation, the integral notation. If you've ever seen in any kind of very mathy movies, you usually see that long skinny S, and that's the integral notation which we're learning today. And that is the limit of a Riemann sum. Whoa, what is a Riemann sum anyway? I never mentioned it yesterday, but a Riemann sum is going to be whenever you take your area beneath the curve, so you've got f of x here, and whenever we take that area and we slice it into a whole bunch of rectangles, that's a Riemann sum. So we're going to add up those rectangles. The addition of those rectangles is the sum. They could be trapezoids, it could be rectangles, however whatever you're adding together to get your total area. And yesterday we talked about using LRAM, using MRAM, or using RRAM, and it turns out for the Riemann sum, the best estimate is not any one of those methods. The best estimate is if you can make it so that you have really skinny rectangles. Notice how big the overhang is when our rectangles are small and are wide, and we have very few of them. And notice with any one of the methods how small the overhang is as we get more and more rectangles under the curve. And you might be saying, well, if a lot of rectangles is good, how many is the best? Why not infinitely many rectangles? And I would say, why not? And how do we do infinity in calculus? We use limits. So that's where we're going. So we have here just kind of a graph of a bunch of rectangles under a curve from x equals a to x equals b. And it's sliced into rectangles. It looks like they used, it looks like they sort of were inconsistent, but let's say they used left-hand rectangles. It actually doesn't matter. So I know it may be bothering you that it's inconsistent, but it actually doesn't matter because there are going to be infinitely many of these rectangles. So who cares which method you're using, because the rectangles themselves, if there are infinitely many of them, are going to be infinitely skinny, so they don't really have a left or a right or a midpoint. It's kind of a infinity challenge for your brain. Okay, so we're looking at this. Remember, this curve that's graphed is f of x. That's this line here. And we're slicing f of x into rectangles, a whole bunch of rectangles. And the rectangles have a height. And the height is basically the y-coordinate, right? So the height is the function. And the height changes depending on where you are as your x-coordinate. It's not always the same. This rectangle is taller than this rectangle, but the function changes with your x-coordinate too, so that's cool. And then your rectangles also have a width. A couple of different ways of thinking about the width. One way of thinking about the width is we could say, well, it's x sub 1 minus x sub 0. We could say, oh, we're going to call that the change in x. Or another way we could think about the width is we could say, well, we have an interval here that is b minus a long, and we're slicing it into n rectangles, so our width is going to be b minus a over n. So these are all the width of the rectangles. That's all different ways of expressing that width. And then the height is going to be f of x. So if I want to add up all of these rectangles, I can do that. So we're going to say, well, our first rectangle is going to have a height. It looks like they used LRAM. So our first rectangle is going to have a height of f of x sub 0. And it's going to have a width of b minus a over n, or delta x. Our next rectangle is basically going to have a height of x sub 1 and have a width of b minus a over n. And so on until we get to our last rectangle, which is basically, and I'm going to be a little sloppy with, like, I know that there are n plus 1 vertical lines here, and there are n rectangles, but I don't have to be perfect with this because there are infinitely many. So infinity plus 1 and infinity are basically the same thing. So I'm going to call this height x sub n, even though it looks like they used x sub n minus 1, because there are infinitely many of them, so I don't have to be perfect. And the width is still going to be b minus a over n. Okay, so in pre-calculus, you learned how to express this sum using sigma notation. Everything is the same for each of my rectangles, except for that little counter. I'm going to call that k. So we're going to start at k equals 0, and we're going to end when we get to n. And so for each of my rectangles, again, this is the height, and this is the width. And the sigma adds them all up. And the way we make it calculus is we say, that's cool. That's cool if you have a finite number of rectangles, but if I want to get the exact area under the curve, the way I'm going to do that is by turning this into a limit as n goes to infinity. Now I have infinitely many rectangles because my counter is going to go from 0 to infinity. And they're infinitely skinny because b minus a over n is going to be basically 0. And you might think, well, if I'm multiplying by 0, then isn't my area always going to be 0? And that's kind of the magic of limits is, you know, sometimes that 0 that we're dividing by winds up canceling, and so it's really indeterminate, and so it's not actually 0, but it feels like it might be. But you can see that we have an area here, so we wouldn't have an area of 0. All right, this now is a calculus way of thinking about the area under that curve. They're no longer actually rectangles because they have a width of basically 0, but there are infinitely many of them, and we're going to add them together. Again, doesn't matter whether we use LRAM or MRAM or RRAM, because they're infinitely skinny, there is no midpoint, there is no right side, there is no left side. So this is your new notation. The new notation is going to change this whole big, ugly awkwardness into that beautiful long skinny s and turn that into a definite integral. And the definite integral is going to be a magical adding tool that adds up infinitely many rectangles, and the rectangles have a height that's equal to our function and a width that's equal to a little tiny infinitely skinny change in x, just the same way it was when we did dy over dx. That was an infinitely skinny change in x. And we're going to have from A to B when we do that. Here's the notation. I just want you to be comfortable with some language here. So the A and the B are called limits of integration. They're where we start and stop drawing rectangles. So here if I have f of x here, A would be the beginning of where I start drawing rectangles, and B would be where I end drawing rectangles. The integral sign is that long skinny s. They're kind of fun to draw, so go ahead and practice drawing them. And then the function itself is called the integrand, which is also kind of fun to say. And then dx, the x part of that, is really a dummy variable. It tells us what we're integrating by, so it tells us what which axis we're slicing into infinitely skinny bits, but it's a sort of a dummy variable because in the end, our answer is going to be a number. Our answer is going to be the area under the curve. So if we do the integral from a to b of f of x dx, that's the same thing as f of t dt. The letter itself doesn't matter. It's just a dummy because the integral is the area. We're going to practice changing these awkward limit sigmas to integrals. Okay, so this part I'm going to do this first one with you. This part, all that magical limit of sigma is going to turn into that long skinny s. The limits of integration for us, this one told us, is going to be from 7 to 10. And then our x-coordinates are changing, but we have x, 8 times the x-coordinate squared, so our integrand is going to be 8x squared. And then 3 over n is, because our interval is 3 wide from 7 to 10 and we're cutting it into n rectangles, that's going to be our width. So this is the height of each of the rectangles. 8xi squared would be the height, and 3 over n is the width. That turns into dx. All right, so that one is done. That's translated from awkward sigma notation into an integral. And now this one is a little harder. So let's say this is the height of our rectangle, and this is the width of our rectangle. So I'm going to just expand this sigma notation a little bit so that we can see it. So our first rectangle has a height of 2 times 3 over n and a width of 3 over n. Our next rectangle has a height of 2 times 6 over n and a width of 3 over n. And our last rectangle has a height of 2 times 3n over n and the width of 3 over n. So it looks like our x-coordinate is changing, and it's changing by 3 over n each time because that's the width of our rectangle. So I'm going to do my magical integral, and my function is 2x. And then my width is going to be dx. But now, in order to figure out what our limits of integration are, we have to remember this is a limit as n goes to infinity. And as we do that, we have our first rectangle is going to be 2 times, if n is going to be infinity, it would be 2 times 0. So we're going to start at 0. And our last rectangle, if we do the limit as n goes to infinity, would be 2 times 3. So our integral is going to go from 0 to 3. And that's kind of satisfying because we wanted our width of our interval to be 3 because that's what we figured out for the width. All right. So this skill of changing our limits into an integral is not totally simple, but you can do it. And that is a summary of section 6.2. 6.3. Have a nice day.